end of the second unit. So here we are going to see the concepts behind this the magnetostatic force. We already discussed about the point charge. When a point charge is moving in a particular direction, how that the direction will be changed in case of presence of electric field and magnetic field. And we also studied that how this magnetic field influence the direction as well as velocity, and also the acceleration with respect to time, how it is influencing. All these things we have already discussed about in a point charge level. So in the next topic which we are going to see, the same force, how it will act on a particular line charge or a surface charge, how it will be affecting. So I believe you already know about the syllabus for that course. And so we are going to learn about this. In this class, we are going to learn about this Ampere's force law and the inductance and magnetic energy. So this magnetostatics, it starts with the Biot-Savart's law, Ampere's law, and we have extensively studied about these two topics. And we have started with the magnetic flux density. So this magnetic flux density describe the number of magnetic lines which are created between the north and south pole, and that integration always will be zero. We already know about that because in a given finite surface, the net magnetic field which is exerting out will be equal to the incoming one. So by the way, the total magnetic flux density will be always be zero in a given space. So in a given volume, if you calculate, then you will get a finite value. So that you have to keep in mind. Actually, we are going to see for the force due to magnetic field, how this magnetic force can be used in different applications. That also we are going to see. For this, we have started with the discussion of the magnetic force on the charged particle. So if a charged particle is available and whenever there is an electric field, then immediately force will be exerted upon that, then the particle will move. Or if the particle is moving in the electric field, then the force can be converted into the total energy consumed. By the way, work done will be calculated. So either way it will be done. So in any case, whenever the particle is moving in a given electric field, either because of the particle itself or the external, so the total work done will be can be calculated. And this is for a electric field. So always the point charge will go in the same direction of the electric field itself. You can clearly see that the Q is going to be the scalar one, the electric field and the force will be in the same direction itself. So the electron will follow the magnetic field path. So if an electron is traveling in a particular velocity, and it will go in the same direction itself because of that. But if it is perpendicular one, then it will always reduce the speed and will got deflected because of that. This we have to keep in mind. The next one is the magnetic field. The magnetic field, it is very similar to that of how this magnetic field is produced. So a particle which is stationary cannot produce any magnetic field. So in the same similar way, the particle which is stationary will not be affected by the magnetic field. So the force will not be exerted upon that. Once it pick up a particular velocity, let's say it is having the velocity of some u vector, and this u vector has 3ax vector plus 4by vector, sorry, ay vector. So then this velocity will give the rise to the magnetic field, and that will give the force exerted upon that. So for this, the velocity is the very important tool. And someone asked about that if a moving charge is deflected by the magnetic field, then it acquire more velocity. Therefore, will it produce magnetic field or not? So that's a good question. We will, on the way, we will discuss about that. Okay. So this is the two important thumb rules of the moving charged bodies. Okay. So this together, which can be added, since we both are completely independent each other, we can very well add each other. And by the way, we will get the Lorentz force equation. And this Lorentz force equation can be studied in different forms when the electric field is absent, when the magnetic field is absent, when both are present, how this force will be exerted upon that, and therefore how this force can be calculated with respect to time. And there comes the space-time continuum concepts will come. So it is very, very useful equations to solve many important problems in the field of charge dynamics, like atomic physics, then motor. In so many fields, actually, we can apply this Lorentz force equation, including the transformer and the electromagnets. So in many concepts, this particular equation will be very, very useful one. I think this example you have already studied, and the in this at the end of that example, someone asked that if a particular, let's say we have this three-dimensional axis, and in this particular direction the charge is moving, therefore it will immediately acquire the velocity, and therefore which we call the current itself. Therefore, this particular current, which is a moving charge, and therefore it's supposed to produce the magnetic field. So it is very simple that you can apply the thumb rule. So you will get the magnetic field, uh, sorry, the magnetic field in the uh, anti-clockwise direction, it will be produced. So that is a very, very simple one. But the same thing when it is going in a clockwise direction, the current itself, that is the charge itself, if it is moving in that, then we can see that it is nothing but a loop current element. So for that, the magnetic field will be completely different, and it will be maximum in this direction. And in fact, this is the same direction of the magnetic field which we have considered. So both will add each other. By the way, there could be a slight increase in the magnetic field. There's supposed to be some slight increment in the magnetic field, which is actually given by external body plus the magnetic field due to the self. So both will add each other. But on the other hand, if this same charge is actually moving in this other direction, exactly it will go in the opposite way. So that are the things you have to keep in mind. But this value, this BS value, will be extremely small while comparing this B. Also highly depends on the velocity, the initial velocity of the charge which is moving. So anyway, it is worth to consider this particular small magnetic field induced by the moving charge or moving charged body, whatever we can say that. So I believe up to this, you have a good idea about how this magnetic field changes the direction of the point charge. And very similar to that of point charge, we can also extend the same study on a current element or a surface current or in a volumetric current, we can see that. So here we have different versions of the currents. And so line current, surface current, and volumetric current, it is available. And all of these currents can be simply tell in this way, that a small charge into the velocity will give us the small current element. And the same thing applicable to volumetric also, you will get the very similar expression. So that is what we are calling as current. In that case, this whatever the if we consider a line, and it is carrying a current I, and at a small length, if we calculate the current, then it is going to produce I into dl. Now this I into dl, we got it is named as current element. And if the magnetic field is available in a particular direction, then if we take the cross product of that, then we will get the force acting upon that. Using the simple using this simple right hand rule, you can easily get the force exerted upon the current element due to the magnetic field. You can easily see that. You're supposed to remember that if the magnetic field is towards the current element, then the force will be in the downward direction. And if the current is actually in this direction, then it will be upward direction. So all these things you have to keep in mind when you apply that. So most of the cases, the it is always people will consider that the magnetic field is towards the paper or towards the screen. In that case, the current, if it is traveling in this direction, then the force will be exerted upon that. Then you can rotate this particular geometry in whatever the direction. If this is the current, then the force will be in this direction, where the magnetic field is towards the charge. If it is opposite side, you will get exactly all the directions will be opposite. That is a very easy way to understand the force which is actually acted upon that. So using this way, we can see that how this force will be exerted upon that, in what direction this force will be acted. Once we got for dl, then we have to integrate over this length. Then we will get the overall force acted upon the line element with respect to that. So this here you can see the expression for this total, and this particular workout, if you do for a closed surface or closed volume or a closed line, then you will get the B force will be a finite value will come. In case of the single element or something, then the current actually will look like it is ended up here and there is no movement at all. So like that, the issues will come. So that is what you have to keep in mind when you work out this particular simple problem. So how we can exactly calculate the force between the two current elements? Okay. So here what you are seeing here is that there are two current elements and both are loops. Both may be any shape of loops, circular or rectangular, square, whatever it is. And now we are going to calculate the force acted upon this. Let's say this is the test current, and this is the source current. And what is actually happening, the current flow on the source current loop is producing a magnetic field. This magnetic field is going to act or going to exert force on the second loop. In that case, what is the total force acted upon the second? And there comes, we can calculate the force acted upon the second one because of the second loop. That actually we can easily calculate. So how to do that? For this, we have to take the small current element. I already said the small current element is nothing but we are going to take a small length and we are going to multiply with the current. So this vector is nothing but small current element. So for this, the very first thing we are going to do is we are going to take the element 1 and we are considering a small length. So we are considering a small length, and this going to be current I1 and the small length L1. So we have this vector. So for this, how much force will be acted if this field is actually coming in a particular direction and the field is created because of the loop 2, and this is actually calculated, this is actually excited by a small current element here. So we are going to have small magnetic field. So because of the small current element in the source loop, that is loop 2, small magnetic field is created. That magnetic field is going to act upon the small current element and going to apply the force upon it. So that is nothing but a small force which is induced upon the loop 1 due to the magnetic field of the loop 2. So this is the easiest way we can easily do it. Now we have to apply what is this B2. So this B2 is nothing but the magnetic flux induced by the current, this line current. So which is very easy to calculate using the Biot-Savart law. So the Biot-Savart law says that the you have to multiply the current element and the R vector, which is the line joining vector. So here you can substitute this the unit vector in terms of this AR12, which can be said as R vector divided by magnitude of R, where this R vector is nothing but the line joining vector between these two small current elements. And this will keep on change as this will change. So this is a variable. The R21 is the variable. The remaining all elements going to be stationary in that particular place itself. So now we are going to substitute this. You're supposed to remember that always we write the Biot-Savart law without this mu naught. But the moment this magnetic flux density comes, we already know that the B is nothing but this mu naught into H. So that is why we have substituted here. And by the way, we got the force. So now after substituting this particular one into this, you got this expression. That is a small force between the two small current elements which are connected by the line joining of R21 vector. And by rearranging this one, we can integrate for both the lines, both the loop lines. When you integrate, then you will get that because of this overall loop, what is the magnetic force acted upon this another loop can be calculated by means of double integration. And for this you have to integrate properly, because if these two are these loop currents are connected, and then you have to do it very other remaining all are simply constants, you can take it out of them. So this three cross products, so this is going to give one vector, this vector, so this force will be always be perpendicular to both the line vectors. So that is what you have to keep in mind, and depends on the shape of this loops, we will get different forces acted upon that. Let us see how to calculate some for a rectangle case or some circular cases, which are very useful for many of the applications. Now let us take some square or rectangle loop. This is the rectangle loop which is drawn, and this is assumed that this is lying upon a particular plane. So let this plane be xy plane. So we got x, y, z, and we have this square. Let's say it is a square. Therefore, all the sides it is going to be same, and the magnetic field is traveling from this particular direction. I'm sorry, it is actually it is traveling along this particular direction, and that is what it is drawn in this way. So here x-axis, y-axis, all these things not available, so that it is completely independent. In other words, we can say that the B, that is the external magnetic field, is parallel to this loop itself. Okay, so since it is parallel to the loop, then but with respect to the current elements, they are actually perpendicular. Therefore, the force will be exerted perpendicular to both the vectors. So since this is actually traveling in y direction and the currents are in the x direction, let's say this is actually in the x direction, then the force will be on the upward direction, that is for a let's say segment 1. So this is the segment 1, this is the segment 2, 3 and 4, like that we can assume. So the segment 1, which is actually traveling, current is traveling in one particular direction, so it is giving in the upward direction. Therefore the same loop current, whenever it is traveling in this direction, so it will give the opposite direction. So you can say that this I1 and I2 are just opposite. So I1 is equal to minus I2, like that, or I2 equal to minus I1, like that. So in that case, the just opposite current flow will, but the magnetic field is in the same direction, will push the loop or the line element in the downward direction. So because of that, how we can draw from the horizontal side. So we have, this is the plane, which is the xy plane. The magnetic field is traveling in this particular direction, and you have this, when you see from this, the current is actually traveling in towards A to C. So when it is traveling towards that, you have to draw like this, and but here it is coming out of the paper from D to B. So it is actually traveling out of that. So this is how we have to draw. In that case, the force will be perpendicular to this, and here the force will be downward. So always there will be a tendency that the force will be going up and down, but the moment it, let's say it is lifting itself because of the force, it is lifting itself up, then this, it is going out of the magnetic field direction. So it will try to show some angle towards that. So this angle once again push back to this, or if the magnetic field is not available in that particular direction, once again it will come to the resting position. So by this way, this this particular loop will start to move in a zigzag manner, or sometimes it will start to go in a clockwise direction, or so that is how this structure is going to behave. So for this, you have to take the cross product of the current with the external magnetic field. Therefore, you can calculate the force acting on that. Now, another important question is, what about the force which is actually on the element or the section 3 and the section 4. So these two forces, if you notice that they are actually in the same direction of the magnetic field. So since they are in the same direction of the magnetic field, so this is, let's say this is along the y direction, then this is actually in the this current is actually in the minus y direction, but here this current is along the y direction. Okay, so because of this, then the cross product is going to be 0. If it is 0, that means this F3 and F4 will be equal to 0, which in other words, along the y direction, if the current is flowing, then there is no effect upon that. So that particular direction, there won't be any movement. The movement will be only along this vertical side direction. But due to this magnetic field, this will start to do like this. So it will this structure will start to rotate in this way. But if you create some shaft or something, it will start to rotate. Otherwise, there is no so-called physical attachment. So it will try to jumble up zigzag manner. It may go. And but if the initial point is having some angle, then always this normal vector of this loop will try to get the calculation. So this angle created between these two will be useful to calculate the force acted upon that. And since the force is calculated, then you can calculate the torque upon that. That means just at time t equal to 0, it is in the rest. But after some few moments, then the when the structure start to move, and at the initial acceleration, which we call the torque. So this torque actually we can calculate. So this is calculated with respect to the magnitude of the force and the width of the line. So this is the width, the total overall width, and this width actually increases. This force will be very high because that it is going to give up more area for that. And then we have the sine alpha. When this alpha equal to 0, so you can easily assume that the torque will be 0. So that initial movement will not be available. Once the initial moment is given, this angle will become non-zero quantity. When the angle become non-zero quantity, you will get that. Similarly, when it is actually 90 degree, you will get the maximum torque upon that. And when it is, so by this way, when we connect to a mechanical structure, this loop will keep on go. Okay, so like this actually that the shaft actually tend to move. So how to get it in the real practical structure? So we need the current source. So this is the current source where the current actually traveling in. This is actually a shaft which actually makes the it will touch this rectangular loop. So the rectangular loop will be like this. And so these assume that here these two are having some wheel or something, so it is connected with another loop. So whenever it is rotated with respect to this axis, anyway it will going to touch that, but the circle is made in such a way that this is positive, this is negative, like that, so that the current will go in this loop. Okay, now once it is done this way, the current will go this way, and this. So anyway, in this particular direction there is no force. The force will be up and down like this way, but anyhow the torque will be 0 at the initial moment. So for this torque only we are giving some starter. So what this starter will be the initially in general we will connect a capacitor. I think you have seen some capacitors in the motors. So this will create a electrostatic force, and this electrostatic force will create some movement in the upside down movement in that internal structure. So this small movement is more than sufficient to give the what do you call this this to make the shaft to move, and the force will keep on go, and the maximum the maximum force it will be exactly when it is perpendicular direction. So when it is in this way, and then once again when it is going in the downward direction, the magnetic field will will give opposing because the current flow is get changed. So both the pushing as well as stopping, both the issue make this shaft in moving in a constant speed. And this is the Walden style motors where the magnetic fields are, in order to make the magnetic field perpendicular, they always keep like this. But nowadays if you see the windings, so you will be seeing 4 sections. So the 4 sections will be like this. Okay, so this here the windings will be there, here the windings, here the windings. So this will create the magnetic field like this and the magnetic field like this. And but anyhow the same principle is applied when you place the structure, this current, this line which is carrying the current and the magnetic field both will be perpendicular such a way that the shaft will move in the perpendicular to both the directions. So by this way we can get more magnetic field compared to this and you'll also get uniform magnetic field in almost all the directions. So because of that your motor will go in a very soft manner without any cranking sound or something else. So this is the primary advantage of having this type of magnetic field. So a magnetic field when it is giving force on a line element, then you will get so many interesting behavior. Just opposite of that, when you do in the presence of magnetic field, when the shaft is moving without current, the current will be produced. That is another interesting part that can be easily solved with the so-called Ampere's law itself. That is what will happen for a current element. Now how we can calculate all these things? So let us take a simple example. So what you see here is nothing but a rectangle loop, and a rectangle loop is placed just away from the origin at a distance of rho naught. Okay, so it is kept in the same plane itself, that is along the rho and z plane. Okay. So in this plane it is kept, and okay, so it is having width of A and height of B. Okay, so this height going to be available along the z direction, and this A will be available along the rho direction. And now you can easily imagine there is a cylinder is available like this way. So you can easily imagine there is a cylinder is coming out of that. There are two cylindrical structures can be used to represent this loop current I2. I will call this a L2, and this is actually going to be the test 1, and this actually got the magnetic field from the I1 current. So this I1 current is nothing but a semi-infinite or infinite long filament. So infinite long filament means it is sufficiently larger than this B, maybe 10 times or 20 times. Total length is very large. So over this particular region, it is going to produce only this 5 component alone. So this magnetic field will be having the 5 component alone will be available. So because of that, this magnetic field is going to travel all the way along this particular direction, will affect all these sections, section 1, 2, 3 and 4. There are 4 sections. All these sections will be linked by this magnetic field, and we can expect there will be a force exerted upon that. Now how to calculate the force, and because of that what could have happened? So that is what we are going to estimate. And here this is like a theorem. So they show that the force experienced by the loop is going to be this. Okay, so in order to do that, we supposed to define the problem in this way, whatever that I told. So first you have to draw the line element, then at a distance of rho naught this loop is kept, and this loop is having 4 sections, yeah, 1, 2, 3, 4 like that, and their dimensions, everything is very important. Now the total force due to the current I1 acted upon this loop L2. Okay, so how to calculate that? So for that actually we are going to just add all the forces. Okay. So there are 4 sections or 4 line sections. We are going to add all these 4. Okay. And this can be calculated by means of this loop, closed loop integration. But anyhow, it is better to calculate with respect to this F1, F2, F3. So first we will calculate F1, F2, F3 one by one. So let's see how to do that. Now let us take only this line section 1 alone. We have this infinite line, and this infinite line is going to take a current of I1, and because of that it is producing a magnetic field, and this magnetic field is going to act upon a section 1 line. So this section line 1 has the total height of B, and the current is actually traveling along the Z direction. In that case, we can simply define this small dl is equal to dz vector, and in order to get the vector you are going to put the unit vector for that. So this is the dl vector, and I2 is the current which is flowing in. Therefore I2 into dz az vector, that is nothing but the small current element. So that is, we are going to substitute for this. And the next one is the magnetic field which is induced. So the magnetic flux which is induced is nothing but because of the first one. So we have this mu h1, where h1 is nothing but the magnetic field induced by the infinite line. We already know about that. So it is nothing but I1 divided by 2 pi rho naught. Okay. And mu naught we are adding to consider the magnetic flux density. And its direction is the phi direction. So that also substituted here. So this is the dl vector, and this is the, we can say that this is the B vector. We are supposed to take the cross product, and over the length we have to integrate. The length is starting from 0 to B. So from 0 to B we are actually integrating. Now it is very easy, because the very first thing we have to do is we have to multiply these two. Okay. Then the resulting one we have to integrate. And first we have to take all the constants whichever is not relevant with respect to z direction. So here you can see that this entire structure is completely independent of the z direction. So first we have to take it out, and the current I already is available. So this can be said as I2 into, so we will write the mu2 and I1 divided by 2 pi rho naught. This all been taken out, and you have two things. One is 0 to B dz vector, and the cross product of az vector into a phi vector. Okay. So now the very important question is how to find out the direction, because the resulting, obviously we know that it is going to be the cross product of the cross product of az vector and a phi vector. We know that it will be a rho vector, but the question is whether it is positive or negative. Okay. So the easiest thing is when you multiply a rho vector and a phi vector, you can see that first row then phi. So this is the order rho phi z, x y z, like that. So when it is available in the same order, you will get plus. But whenever this exchange is taking place, let's say a phi vector cross a rho vector, this order changes, then the resulting will be nothing but the negative term. So that is what the simple thumb rule, when you apply you will get it. So you will get the negative value. So that is why this negative sign is coming. Remaining all terms are available. Then when you integrate over the z, you will get B value. So the B is available here, and the resulting a rho vector, which is perpendicular to both z and phi direction, with the negative symbol. So this is the force acted upon that. So the force will be acted in this direction. Okay. So this is the rho direction, but opposite direction the force will be acted on that. In the very same way, we can easily calculate for this element 3, because for both the magnetic field, the concept is going to be the same, and the integration is going to be same. but only the current direction is opposite, and the field will be acted after this rho naught plus A. So that is what we are going to calculate second. So this F3 is nothing but the force, the magnetic field actually is coming in this particular direction. Let's say this is the B1 vector. So what is this value is nothing but mu naught I1 divided by 2 pi. This is actually rho naught. This is going to be A. So rho naught plus A. So this magnetic field is supposed to be used here, and this dl2 vector. So this is the small dl we have to take. So which is nothing but minus dz vector, dc into az vector, because the current is actually traveling in the opposite to z direction. So that is why we got it. So when you substitute this to the cross product, still you can see that this is az vector cross a5 vector. You will get negative, but this resulting negative and this already existing negative will be cancelled each other, and you will get positive value. So you will get a positive value. So that is nothing but F2. So the force 3 will be exactly along the same direction of A5 itself. And then we can easily calculate for 2 and 4. So 2 and 4, both the magnitude will be exactly same, only the direction is going to be opposite. So it is very well know that if it is same magnitude but opposite, they will cancel each other. But let's see how to evaluate that. So here we have this line vector, and at a particular distance rho naught, we have this section 4. And for this, the dl vector is going to be d rho into a5 vector. Okay. Now we have to take the cross product with the b, what is actually coming into the picture. So the b value is very well known. With respect to rho, it is going to change from rho naught to a plus rho naught, and this d rho a5 vector is coming from this dl vector. We are going to take the cross product of that, and then you will get the this integration you have to do. So here you have 1 by rho into d5, sorry, d rho vector is coming. So obviously you will get ln will come, and when you substitute that, you will get the minus value will be accounted for this when you multiply these two. So the resulting vector will be in the z direction, and here I think there will be a minus term will come. That is why it is exactly upside down, and you will get that. But if you calculate the fourth one, you will integrate in the same way, but you will get the negative because the current is in the opposite direction. The force will be exerted upon that. So since F2 magnitude and F1 magnitudes are F4 magnitudes are same, then they will cancel each other. So this F2 and F2 will cancel each other. You will get zero value. So simply this FL, that force acted upon the loop, is nothing but F1 plus F3 alone. When you add this, you will get this vector. Since both are available in the rho direction, the force also will be either it will be positive or negative. So this is highly depends on currents of the first loop, second loop, and the length of the width of that loop, and the length of the loop, and its position. Everything matters. So by all these together, when you plot with respect to, let's say, the force with respect to rho naught, when you try to calculate, so you will get it is decreasing one, but this rate of this will change with respect to a and b value, and I1, I2 value, everything accounted here. So you will get some interesting behavior. So you can make it positive, negative directions all the way. It is quite visible. So this is how you have to calculate the force acted upon a particular loop or a particular line, or a particular even you can calculate for a particular area, for a surface current. All the way you can easily calculate it. Now the same question can be asked in another way, that if we have an infinite sheet, then how this how this force could be. So we already know that if it is infinite, then the magnetic field will be available only in the perpendicular direction. Okay, you already know about that. By Ampere's law, we already calculated that the magnetic field will be available only in the either side of that, and at any distance you will get the uniform magnetic field throughout the case. So then we can easily see that this current is same as that of the magnetic field. So it may not, F2, F1 and F3 might be 0, but on the other hand you can see that this two currents are perpendicular to that. So there could be a force acted upon this particular direction. So some interesting behaviors will come. So you can expect such a questions in the exam. Just note down that. If you have any questions upon that, you can very well ask. Now we will complete the last part, that is the magnetic induction. So we already know that what is meant by induction, that is nothing but adding up or rising up the particular structure by including more things. So in case of magnetic induction, it is nothing but by means of connecting magnetic fields by proper way. Since it is a loop one, you can easily link them up, and you can also increase the magnetic field lines, and by the way magnetic flux density can be increased. So this way of increasing the magnetic flux density by means of stacking the structure or by means of connecting them in a proper way for a given structure, so that is we call magnetic induction. So here we already know about that. Whenever there is a loop, then it will be having magnetic field like this. It will be available in the center. You will be having perpendicular direction. Now you are going to bring another loop current in this particular direction, so obviously it will be having in the same direction. You will get the magnetic field, and you will get like this. By placing this distance in such a way that you will get all these lines will be linked up, so that you will get the total magnetic field will be like this. So in other words, if individual loops are creating magnetic flux of H naught, then after adding them you can expect twice that of the H naught. Okay, so here what you have done, by properly selecting the spacing between these two loops such a way that you have connected all the loops, or you have linked all that loops, and you got it too. Similarly, if you have n number of loops, then you can expect n into H naught, and this phenomena we call that as the induction. In some other books you can find the word called linkage. So it will be called as magnetic induction or magnetic linkage or magnetic flux linkage. So because of the magnetic flux linkage, the total flux is often calculated as the magnetic linkage lambda, which is nothing but n number of turns into this the magnetic flux induced by the single turn. So total you will get huge amount of magnetic field or magnetic flux density will be created. That is often referred as simply total magnetic flux linkage. So it is once again the same magnetic flux only. They are giving new name to tell that all these field lines are inducted or connected or linked such a way that to produce the huge amount of magnetic flux. And now this is all happening because of the current actually flowing here in this structure. Okay, so this current and how this total linkage, how they are connected. So this is actually connected by means of the how this induction is induction is characterized. So that is why they have linked by means of a proportionality constant, which often referred as inductance. Okay, so what is meant by inductance is nothing but ability to make the flux linkage. So this cannot be happening for all type of structures. Only by means of selected structures only it could be done. The very more proper one is the helical structure. So we can see that many loops are in a vertical axis. It is being connected. So all the currents more or less same, and at least at the center you will get the strong magnetic field, and you will get the overall magnetic flux linked by this way. Okay. So this phenomena often referred as the linkage, and this proportionality constant is named as inductance. Actually, this inductance name was given by one of the famous scientists called Oliver Heaviside. But many people do not know him, even though he has written one of the very important books, which still we follow as the textbook for the electromagnetic field theory. And he has introduced this very important word, inductance. And this inductance, uh, whichever the structure is doing this inductance, can be taken as an inductor. So that is why inductor means people always draw this way. We can do this inductance in many ways. For example, if you put a magnet in the center, it will create still more high magnetic fields. It can be produced. So that is the same structure can be also called as a inductor. There are multiple ways we can do that. So this inductor often specified by this letter L to name the word linkage. So the inductance can be calculated by the total magnetic field of the total magnetic field created by this inductor divided by the current which is flowing inside. So that is often referred in terms of Henry. So the most common reference value is nanohenry. Now this is actually, we are thinking about single loop. We can also create multiple loops, and we can create the flux linkage between the loops also could be possible. And that kind of inducting or that kind of linking procedures often referred as mutual inductance. Also in some of the very old textbooks you can see that mutual linkage. So this often comes with the so we have two possible, because of this loops there are two possible things can be happening. One is the self inductance or the self linkage, and the mutual linkage could be possible. So this is described by two fields. One is psi11 and psi12. So psi11 is nothing but self, and this is actually mutual. So you can connect this current, whatever the current is flowing through that, you can easily connect with that by the L1. So L1 we can say that is nothing but psi11 divided by I1. And the same thing for the second circuit, where L2 is nothing but psi22 divided by current I2. And there is a mutual linkage between them. So that is actually a little interesting one, that can be calculated by with respect to current I1 or I2. But if this is the source one, which is actually calculated, the loop currents are determined by the circuit one, then that should be used, because this is going to induce the magnetic field. Because of the induced magnetic field, I2 is going to be produced. So this is why in the opposite direction also it is very much so, because the structure, whatever the structure you have is completely reciprocal structure as well as symmetric structure. So the magnetic flux linkage from 1 to 2, 2 to 1, both supposed to be same. And nowadays this particular structure used as a transformer, so people use some transformer oil. If the transformer oil is linear, then that, otherwise some polarized materials will stop the magnetic field in any particular direction. So that is very that kind of property is very useful in many communication purpose. Maybe in the communication purpose we can study about such structures, which often referred as isolators. So they will allow the current flow from this circuit to this circuit, but not in this opposite direction, which means that it allow M12 but not allow M21. M21 will be 0. So that kind of material is also available in the world. So they are extreme magnetic materials. We will see those things maybe in the magnetic material. When we study about magnetic materials, we will study about that. At last, we will finish with the magnetic energy. So the magnetic energy is nothing but the magnetic field, how far it is stored by a given structure. Since the magnetic field or magnetic linkage is often related with the inductance, so people always calculate this total magnetic energy stored by the inductor as 1/2 L into I square. It is very same as that of the capacitor. For the electric flux, this can be calculated by 1/2 C voltage square. So this is the magnetic field and electric field stored by capacitor and inductor respectively. And for a mutual inductance structure, we can use this calculation. Ultimately, what we are actually doing, we are actually integrating all the field lines and taking average for that. So that is what the average energy stored by the structure. The same thing applicable to magnetic flux also. And using this, we can calculate inductance for many different structures. I am leaving these concepts to you, so it is very, very simple one. And the interesting part is, like, if you take a small wire, when there is a current flow takes place, itself will produce the magnetic field. Obviously, by increasing the length and decreasing the length, you can get the self linkage could be possible. Is it? So this self linkage, once you have calculated, then you just divide by current, then you will get the inductance. So that kind of inductance could be possible for a simple wire itself. They are called wire inductors. And if you make it as a helical shape, then you will get spiral inductors will come. And we can also create inductors in this way, like the structure will come and it will go in this way. This is called spiral inductors. So here also the magnetic linkage will be taking place. And not only this, there are several methods. For example, if you take two structures where the current is actually current is going in one direction, another is coming. So there could be a possibility of magnetic inductance can be possible. So there are multiple ways we can get that. For all these structures, you can see in the inductance calculator for that. So finally, you have here the slab. For slab also, magnetic field is possible. So if you have a slab separated by there are two slabs, they are actually separated by distance d, and they are having this has the length L. Then because of this length L, you will get magnetic field, and because of the separation between them, you will get the electric field. Okay. Electric flux density, magnetic flux density. So the structure can produce both inductance and capacitance. By the way, it is very well useful for the tuning elements, because the tuning element can produce the resonant frequency of naught is nothing but 1 by 2 pi root LC. So this is a simple tuner element which we can see in many places. That I hope you have seen in the olden type radios, that after this amplifier there will be a tank circuit will be there, inductance and capacitor will be there. So how this will be realized? There will be a spring-like structure, and followed by there will be a plate will be there. So this plate distance actually we will move. So whenever the knob is moving, this plate distance will change. By the way, you can change the capacitor, and the same knob can be used to shrink and lengthen the spring part. So by the way, you can simultaneously tune LNC. So when you change the LNC, you will get the resonant frequency. By the way, you can select a particular station. So this is how in very olden days people have done that without the knowledge of any computer, mobile phone, anything else. They have beautifully designed extraordinary systems, including wireless systems and wired systems. So I believe you got the various aspects of the magnetostatics. So we have studied electrostatics and magnetostatics. So that is going to come in the exam. Kindly start to study. The next class I am going to give the overall view about that and various numerical problems. And what are the numerical problems available in book 8? Because in that book actually I haven't shown that. I will show some of the interesting examples from simple to big problems, and that will give you some idea that how these questions could have been asked. You can leave the class now if you have any other work.